This conference will now be recorded.
Our speaker today will be Kirk Smith. He is a supervisory physical scientist that has been with the USGS for more than 30 years, during which time he has conducted numerous studies in the field of stormwater and urban hydrology. He specializes in the design and construction of integrated water quality monitoring and sampling systems for the study of time variable water quality contaminant sources in both surface water and groundwater. Thank you for joining us, Kirk. Please take it away.
Thank you, Elena. Good afternoon, everybody. So I'm going to discuss or present a recent multi-year study to determine the relative difference between highway runoff quality from a section of open graded friction coarse pavement and traditional hot asphalt that was done in cooperation with Massachusetts Department of Transportation. The presentation will include a description of the open graded friction coarse pavement and the study design, an overview of the monitoring methods, the results for the sediment loads and particle size distributions we observed in the highway runoff, and changes in pavement permeability and loads of chemical constituents measured in the highway runoff. So as many or all of you know, open grade friction coarse is a type of permeable pavement. It's been around for quite a while. Oregon was the first state to experiment with it back in the 1930s. There were various formulations of open grade friction coarse pavement that have been used throughout the US and parts of Europe for many decades since. In this study, the open grade friction coarse pavement mix contained an air void content of about 15%. 90 to 95% of the aggregate mix was between 2.36 and 12.5 millimeters in diameter, and the open graded layer was about 1/10 of a foot in thickness. I'm sure, again, everybody knows how this works, but open graded friction coarse is a layer on top of a section of traditional, more impermeable hot asphalt mix. Water does not percolate into the base of the road, but instead percolates laterally to the edges. There's been many benefits demonstrated by this type of pavement, including reduction in nighttime surface glare, undercarriage wash-off, reduces hydroplaning risk, reduces vehicle spray, and noise as well. This is a photograph of our study site taken shortly after the pavement was applied. As you can see, the hot asphalt on the right, you can actually see some standing water there where it does not exist on the open graded section on the left. In addition to these safety benefits, there have been numerous studies done in parts of the country and elsewhere that indicate that there are also water quality benefits from the open graded pavement through reduction of sediment in the runoff. This study was performed to evaluate the potential water quality benefits of this type of pavement in Massachusetts because there are differences in the various formulations used across the country, and the climate of the Northeast is much different than where many of the studies have been conducted previously in the southern states, notably Texas and North Carolina or South Carolina. The primary objective of this project was to calculate annual loads of sediment for each section of pavement for over a 3-year period, which differs from other studies that generally compared or contrasted paired storm event results. As part of this study, the Massachusetts DOT modified an existing highway resurfacing contract to specifically incorporate a highway-wide section of HMA across all 4 southbound travel lanes on Interstate 95 near Needham, Massachusetts, into what otherwise was a highway containing all open graded pavement. As a result, the study included concurrent collection of data from the 2 pavement sections with identical traffic volume, maintenance, and weather conditions. Average annual daily traffic volume at the study site was 155,000 vehicles per day, and which is more than 2 times greater than sites conducted in Texas and North Carolina. The monitoring sites were designed to measure the entire sediment load conveyed off each highway section. Concurrently with highway resurfacing, a 72-foot pre-slope fiberglass load-rated graded trench was embedded into concrete at the edge of the pavement at the open graded and hot asphalt or hot mix asphalt sites that collected flow from all travel lanes and the breakdown lane. The highway berm area adjacent to the trench sloped away from the trench system, limiting the trench only to pavement runoff. Water from the trench was conveyed to a prefab manhole with an integrated weir box. By placing the weir box below grade in a more thermally stable environment, we are able to monitor and sample the runoff excuse me, year-round for every event that occurred during the monitoring period. Monitoring was conducted from October 2018 through September of 2021. Water level discharge, specific conductance, water temperature were continuously monitored in the weir box during every runoff event. Water samples were collected from the outlet of the weir boxes during runoff events by a bank of 3 automatic samplers at each site. The weir box was purposely selected given the measurement accuracy of the device and the presence of the sump, which was important to capture the coarser sediments. Ideally, the automatic collection of samples from the weir box inlet would have been preferred, but given that the range of flows was generally small, and under such conditions, the coarse suspended sediment load is generally not proportionally distributed across the vertical water column, the sample collection would have resulted in positive bias without the use of a mixing device or a positional dip sampling arm, which were not practical in a small 6-inch pipe like this. Conversely, fine sediments generally are well distributed in the water column, regardless of the flow rate, and the collection of representative samples is more easily obtained. As such, water samples were collected from the outlet pipe downstream of the weir box. In addition to the suspended sediment collected from the automatic samplers, sediment retained in the weir box and any sediment that we were able to retrieve from the trench were also collected annually to determine the entire sediment mass at each site. Measurements of air temperature, precipitation, snow depth, and wind direction and speed also were monitored as part of this study, as well as we use non-contact sensors to monitor pavement temperature and pavement conditions. Pavement conditions, for example, being dry, damp, wet, the presence of snow on the pavement. Finally, we also measured the permeability of the pavement on the open graded friction site twice a year to monitor changes throughout the study period. The presentation focuses primarily on the comparison of sediment loads, but the report includes a discussion of all these data collected during the study period. This is an example of the sampling schema we use for the collection of the water samples. Runoff samples were collected by a bank of automatic samples on a flow proportional basis. Each sampler is configured to hold 24 polyethylene bottles. This example illustrates the sampling process where each subsample represents an equal volume of flow. As flow increases, the time between the collection of these subsamples decreased. 7 subsamples were composited into each 1-liter bottle. When the bottle was full or the storm ended, the sampler would advance to the next bottle or next sampler as needed. If any kind of error occurred, the system would automatically advance to the next sampler. Each sample bottle was submitted for analysis of suspended sediment and particle size distribution at a 63 micron and 250 micron size break. For 15 storms, a separate sampler at each site concurrently collected a composite sample that was analyzed for concentrations of major ions, nutrients, and total recoverable metals. Over 12,000 subsamples were collected to characterize event mean concentrations during a 3-year study period. At the open graded friction site, samples were collected during 168 runoff events with over 1,000 subsamples submitted for laboratory analyses. Of these 1,000 samples, they represent about 65,000 or 6,500 subsamples. Runoff events were designated as a pier of flow followed by a 6-hour period of no or marginal flow. In some cases, we'd have some minor weeping from the weirs, which did not produce enough flow to physically pull a sample. At the open graded friction site, as I mentioned, 168 events generated sufficient runoff for sample collection, while 226 events were sampled for the at the hot mix asphalt site. Although both sites experienced the same weather conditions, runoff from some sites did not exceed the physical discharge trigger to trigger the sampler, and some events measured at the open graded friction course site encompassed multiple sampling events because the hydrograph lag extended into a subsequent runoff event that occurred during the same day or within hours within that 6-hour period. The box plot shows the distribution of the EMC's event mean concentrations collected at each site. The median event mean concentration for the open graded site was 15 milligrams per liter, which was about half of what was observed at the HMA site. These EMCs were used with discharge data to estimate the suspended sediment load portion of the total sediment at each highway site. Because of the sampling location, these sediment event mean concentrations largely represent fine-grained particles not retained by the weir sumps. Sediment concentrations in water samples only represent part of the data collection. On an annual basis, the entirety of the sediment trapped in the weir sumps and anything we could pull out of the trenches was removed and dried to a constant weight to determine the total sediment mass. Sediment were then sieved into 6 particle size bins ranging from less than 63 microns, the silt and clay size range, to gravel. Subsamples of this sediment also was analyzed for selected concentrations of phosphorus and total recoverable metals. The suspended sediment load and the sump and trench loads were combined to estimate the annual load at each site. While the sediment load was always greater from the HMA pavement, the difference in the annual sediment loads were greatest during the first 2 years of the study, but became more similar in magnitude in the 3rd year. The sediment load, consisting of the very coarse sand and gravel, was higher from the open graded friction core site than from the HMA in the final year of the study, indicating some potential effects from raveling of the open graded friction course pavement, where we were picking up those larger pavement particles. During the 3-year monitoring period, the load of sediment less than 6 millimeters in diameter from the HMA section was about 41% greater than the load from the open graded friction course pavement site. Discounting the coarser gravel size material, the load of sediment less than 2 millimeters in diameter, this would be everything from silt and clay to sand, was 49% greater at the HMA site. The greatest difference in loads between the 2 pavement segments were in the particle size ranging less than 2 millimeters, indicating that these particles are retained by the voids in the open graded friction course pavement. The silt, clay, and very fine fraction of the sediment, these would be all the particles less than a 1/4 millimeter in diameter, discharged from the pavement, represent about 31% of the total load at the HMA site and about 26% of the total load we measured at the open graded friction course site. As I mentioned, the raveling of the open grade pavement material may have contributed to the higher load of particles in the gravel range that was particularly noted in the 3rd year of the study. Semi-annual permeameter tests were done in the breakdown lane and first travel lane of the open graded segment during the first 3 years of the pavement life using a Gilson falling head permeameter. Generally, about 13 measurements were made in the breakdown lane and the travel lane during each test. Permeameter was maintained in the travel lane longer than in the breakdown lane, where it decreased by nearly 2 orders of magnitude over the first 3 years of pavement life. The decrease in the breakdown lane likely is related to the lack of traffic and associated hydraulic flushing. Permeameter in the center of the first travel lane decreased by about 53%, and permeameter in the tire track area of the first travel lane decreased by about 83% during the study period. Based on measurements made by the non-contact pavement sensors, we saw measurements of standing water conditions recorded by the pavement condition sensors initially were 5 times less frequent in the open graded friction course site, indicating that the runoff was draining into the open graded layer as designed when the pavement was new. However, by the end of the project, the difference between the paired measurements on each pavement type was not as pronounced, and in some events, wet and standing water conditions were recorded more frequently on the open graded friction coarse pavement than on the hot asphalt pavement, which were possibly exaggerated by the much lower permeability of the breakdown lane, possibly impeding the flow of water on the porous pavement. As part of a separate subsequent project with the University of Massachusetts Dartmouth Highway Sustainability Research Center, additional permeameter measurements were made from October 23 through August of 25. These data indicate that even after 7 years, the permeameter continues to decrease across the measurement point, with some minor plateauing in the permeability, a little bit of flattening out and a little bit more variability. In addition to the collection of suspended sediment, flow proportional composite samples were collected for analysis of phosphorus and total recoverable metals for 15 events. Together, loads of phosphorus and total recoverable metals in water flowing past the weir box were estimated from discharge and the average event mean concentration. And combined with the phosphorus and total recoverable metal loads derived from the sediment and associated chemistry of the sediment retained in the weir box and trench at each site. The total constituent loads were between 7 and 64% higher at the HMA site for most constituents, except for arsenic and zinc, which were higher at the open grade friction coarse site. Pavement leaching tests done as part of this study indicated that dissolved arsenic and zinc concentrations were about 104 and 122% higher in the open grade friction coarse pavement sample, and potentially explain why the open graded pavement did not necessarily reduce these load values. The higher concentrations may be explained from continuous constituents leaching from the asphalt rubber binder, created in part from vulcanized rubber processed from automobile and truck tires that tend to be sources of zinc. The difference between the chemical loads were not as large as expected, in part because the load associated with the finer grade sediment particles was only about 6% less than what we observed at the HMA section. Concentrations of phosphorus and most of the total recoverable metals that we had analyzed on the sediment were up to 6 times greater in the particle size class less than 25 microns compared to the coarser sediment fractions because of the inverse relation between sediment surface area and sediment grain size. As a result, much of the chemical load exported from the highway sites was associated with the silt and clay particles or in a dissolved or complex form. As part of this study, we also estimated de-icing element loads, specifically for chloride. Concentrations of chloride and loads were derived from relations between specific inductance and chloride concentrations, and cumulative loads were calculated from estimated concentrations and instantaneous discharge data. This figure is an example of a comparison of the cumulative loads for a winter runoff event in February of 2020. Initially, we theorized that the open graded pavement might slow the release of dissolved salts and result in lower peak concentrations, which in turn could possibly result in fewer acute chloride exceedances in receiving waters. But in general, the peak concentrations were not all that different from what we observed on the HMA site. However, concentrations of chloride did run off from the pavement surface much quicker than was observed at the open graded site. And more interestingly, the event loads of chloride from open grade friction coarse pavement often were larger than what was measured at the HMA site, suggesting that more of the salt stayed on the pavement, possibly a result of less salt bounce during the application on that type of pavement, or because of the macro texture of the pavement retained the salt better. Our non-contact highway surface condition data measurements, also reflecting snow and ice collected as part of this study, also were measured nearly twice as often on the HMA pavement as the open graded pavement under the same application of sodium chloride. This is kind of interesting because there's always been a dispute of some sort comparing and contrasting open graded to traditional hot asphalt regarding winter condition data. Many people believe that the presence of salt or that open graded friction coarse pavement tends to always look white and maybe not necessarily treated as it should. Data collected as part of this project does indicate that looks can be deceiving, and that the actual pavement characteristics are or appear to be safe as HMA, or if not better. So in short, the study demonstrated that the open graded friction coarse pavement layer provided measurable sediment load reductions, but this effect decreased within 3 years of application on a high volume multi-lane highway in the Northeast. And although open graded friction coarse continues to capture sediment throughout the 3-year period, fine-grained sediments, which often contain higher concentrations of associated metals and phosphorus, are not completely retained in the permeable layer. As mentioned, we collected a substantial amount of data during this project. I've only just touched on what is available. For the full report and accompanying data releases are provided at the links below if you are seeking more information. Otherwise, this kind of concludes the presentation here.